class, this is the first video of our last unit, Sound and Waves. And this video is on topic E1, Vibrations and Wave Characteristics. So throughout this unit, I want you to think back to if you've ever played with a Slinky. So a Slinky can be used to create at least two different kinds of waves. And it may help to visualize that Slinky throughout our examples. So in the first half of today's lesson, we're going to talk more qualitatively and learn what is a wave and what is sound. And along that path of learning, we're going to learn new terms: vibration, amplitude, mechanical wave, medium, transverse wave, longitudinal wave, compression, rarefaction, sound. This is a very term-heavy unit, if you haven't already imagined already by this long list. And tools like cue cards or Quizlet would be really recommended. In the second half of this, we're going to get into more details, and we're going to take measurements and do calculations. We're going to learn about the universal wave equation. So the word universal should tell you how useful it is. It's universally applicable to all waves. So we're going to be using it in grade 11 and grade 12. So it's really important that you know the relationships and how to use it. Recognize factors that affect wave speed, understand quantitative and qualitative and quantitative relationships between air temperature and sound. And through that, we're going to learn these new terms: crest, trough, wavelength, phase, shift, period, frequency, and wave speed. So let's get started. So this unit is about sound, and sound is a wave. But before we define wave, the definition for wave has the word vibration in it. So before we talk about a wave, a vibration is a cyclical motion of an object about an equilibrium point. An example is a grandfather clock pendulum. And it is predictable cyclical motion. So this pendulum goes to the left, then back to the center, then to the right, then back to the center, back to the left, back to the center. The equilibrium point would be here. A pendulum is an example. Another would be a spring bouncing up and down. Amplitude is the magnitude of maximum displacement from the rest position. It's when the motion, so maximum displacement from the rest position. So far to the right to the equilibrium point. So this distance here is amplitude, or maximum displacement to the left to rest is your amplitude. So this is sideways vibration compared to this vertical equilibrium. We could also have this horizontal equilibrium position. And then if we push up on this object and let it bounce, we've got the maximum displacement up or the maximum hanging point down from the equilibrium. So you can measure amplitude in different ways depending on what your wave or your vibration looks like. When a motion repeats itself at regular intervals, it is periodic or simple harmonic motion. So let's say every time this this pendulum goes from the far right to the left and then back, if every time that takes 3 seconds, then it's called simple harmonic motion. We know in reality, if we do something like this, it's not going to continue in that motion forever, but so it's never, it's a theoretical concept, but we know that maybe if we set this up, maybe for the first 10 swings, it will be close enough to simple harmonic motion. So just a reminder that a vibration is cyclical motion of an object about an equilibrium point. But what happens if that object that is vibrating is connected to its neighbor? And really all matter, if you go down to the particle, whether you're talking about an atom or a molecule, they are really connected to neighboring atom or molecules because of intermolecular forces. You could be talking about neighboring ropes on a string or neighboring loops on a slinky. So what happens when there is vibration of one part of matter? Well, when that first object moves, it starts transferring kinetic energy to its surroundings. And we can actually transmit the kinetic energy along the line of this, maybe this is a string of ropes on a string. So let's take a look at if you were to take a slinky and one side were to be attached to a wall or held by someone that is not moving. And on the other side, you would raise your hand up above the equilibrium and then down below the equilibrium. You would be, and if you were to repeat that action continuously, you would be sending a wave down the length of this slinky. So there is a little gizmo that is helpful in a few things that we looked at, we will look at in this unit. So I'm just going to pull that up. So in this, oops. Interesting. Okay, there we go. So in this gizmo, I decided to turn show rulers, show grid, and I'm going to press play. So I'm going to send a wave down the length of this slinky. In this particular kind of wave, the mass is moving up and down, and it appears that the energy is moving to the right. So the kinetic energy of one object is being transferred to the object to the right of it, or to the base of the slinky. So this is one type of wave where mass moves 90 degrees to the direction of the wave motion. Okay. So now that you know what a vibration is, let's talk about a mechanical wave. So a vibration can move through material, and a mechanical wave is the transfer of energy through a material due to vibration. The material in which that wave in which the energy is transferred, the material, the stuff, is called the medium. Oops. The medium is the material through which that wave moves. So when we're talking about a water wave, the medium would be water. To transfer mechanical waves, vibrations need a medium. So this is not true of all waves. Not all waves need a medium. Electromagnetic waves do not need a medium, but mechanical waves do require a medium. And the medium can be solid, liquid, or gas. The medium density, and therefore temperature, and elasticity determine the speed and distance of the wave in this medium. For rigid materials, waves are transferred efficiently, faster and farther. So for example, an earthquake, as the energy is transferred through the rock of the earth, that happens very efficiently. So that's why you feel the effects of an earthquake very far from the fault lines. Less rigid materials transfer waves less efficiently. So those waves move slower and less distance. If you think of like, if you were making your bed and you hit your pillow, you could create a wave, but very quickly it would dissipate. So there was a little, like a little simulation here. So let's say you were at one end of this long hallway and your friend, is at the other end, and you bang on these pipes and you say hello at the same time. What do you think your friend is going to hear first, your voice or the hitting of the pipes? So pause this and think about that. So if you said that they will arrive, the sounds will arrive at the same time because you speak and hit the pipes at the same time, you would be wrong. The sound actually does not travel at the same speed through solid and gas. So through the solid, which is a rigid material, the wave is efficient. The wave transfer is efficient. And so you're going to hear the pipes being hit, And then after a delay, you're gonna hear the sound. Sound is a wave, an example of a mechanical wave. And sound follows these rules. So all mechanical waves, the wave speed is determined by the medium, what the medium is and what state that medium is in. Let's talk about different types of waves. We have a transverse wave where the particles vibrate perpendicular, that's 90 degrees, to the direction of flow of energy. So that's like your Slinky, where we're moving it up and down, and it's horizontally transferring the energy down the length of the Slinky. Longitudinal is another type of wave where the particles vibrate parallel to the flow of energy. So now instead of moving the Slinky up and down, what if you send a pulse, if you compress the Slinky and then release the compression quickly? So let's show the two. So you move your hand up and down for a horizontal rope, you're gonna send a transverse wave down it. But if you move your hand left and then right on a Slinky, you're gonna start a longitudinal wave. So here are some animations, just to kind of visualize it, seeing the difference. Okay, so for a transverse wave, examples are pendulum, guitar string, or waves in a rope. So here is a transverse wave. Now, just like when we turned off the lights on the Gizmo, you can see that the objects are just moving up and down, and it's the timing of that up and down that makes it look like the objects are moving to the right, but the objects are actually not moving horizontally. It is the kinetic energy that is transferred along to the right. So we say the direction of wave travel, so it kind of appears that the objects are moving that way, but we know it's just the energy that is being transferred that way. We can draw, actually regardless of the type of wave, we can always draw a transverse wave to represent it. With a transverse wave, there's different features that we're gonna label. So there's the direction of the particle motion, the direction of the wave. There is a crest, an equilibrium point, one wavelength, amplitude, trough, and node. We're gonna go over these points in a lot more detail in the second half of this lesson. Okay, now taking a look at a longitudinal wave. An example of a longitudinal wave is sound. Since that's the focus of this unit, we need to know, have very clear understanding that sound is a wave, and it's specifically a longitudinal wave. Specifically, it's a mechanical wave. It requires a medium. The medium of sound is air. So when a speaker is producing sound, it is compressing the air molecules close to it, and the compression gets transferred to the right, even though if we actually take a look at air molecules, we've got the air molecules just vibing, like oscillating from the right and then back to equilibrium and then to the left and then back to equilibrium. So we can trace the wave. We trace the compression along the horizontal, but if we look at the particle motion, it's not moving very far. It's just oscillating right and left. So for a longitudinal wave, they're a lot trickier to draw. You can represent longitudinal waves by lines, and the line density tells you the compression of the air or the substance. So where the lines are all bunched up is a compression. Where the lines are not bunched up, they're most spread out, that's called a rarefaction. So the compression is kind of like the analog of the crest, the high point. The rarefaction is like the trough. And again, we're gonna go over these in more detail. One wave length, like the length of one wave. So a longitudinal wave, here's an example. We've got energy transferred from mass A to mass B, then mass B to mass C, and so on. The particles transferring energy, the springs or the masses, all move parallel to the direction of flow of energy. So if you were to truly sort of take a picture of a longitudinal wave, this is more what it would look like, not the lines, but a smooth gradient from high pressure to low pressure. Compression is a region where medium's particles are closer together. and rarefaction is a region where medium's particles are farther apart. So what is sound? Sound is a sound is a form of energy produced by a rapidly vibrating object causing a longitudinal wave which is detectable by sensory organs such as the ear. Let's say you hit the membrane of a drum, and that drum membrane is going to vibrate up and down. And in doing so, it pushes against the air just above it, causing a compression of air, and then that compression of air spreads out in the room, and eventually your ear actually detects the compression of air because your eardrum goes in and out based on the air compressions. As long as the air compressions are received at a certain rate over time. If you have ever sang in a choir, you might recognize this. It's called a tuning fork. So normally when you're singing with a musical instrument, most songs that you would sing as a choir, there's going to be a few bars of music before people start singing. And that kind of calibrates where you should start. It kind of like gives you a cue as to what note you need to start on. But when you sing a cappella and there's no instrument to set you up for a key, a whole bunch of people starting to sing, they could start on totally different notes. And so when you're singing, I cannot sing, but when someone who is good is singing, it sounds good when the intervals are correct. So the number of steps from one note to the next sounds good based on what it should, based on the song, but also that you have the notes accurate. So if someone says you're pitchy, you're too flat or too sharp, that means you're starting on the wrong note. It's a little bit too low or a little bit too high. So a little bit low pitch or a little bit high pitch. So if a whole room of people in a choir were to start a song on a different note, slightly different notes or very different notes, it will not sound good. So maybe a choir director will take out this thing called a tuning fork. They will go to a piano if a piano is available and press a key and say, okay, we're going to start on that note. But if you don't have an instrument around, you can use this, which can go in your pocket. You hit the tuning fork. Oh dear, this is not the slide with the animation. But anyways, we're going to come to that next lesson. The tuning fork prongs go back and forth and compress the air between your ear and the prongs. So we're going to come back to this tuning fork, and we're going to come back to a lot of different properties of sound. But for now, I want to go back to talking about mechanical waves in a little bit more detail. So do you remember, pause this video, do you remember the two types of waves we've covered so far? Hopefully you're on pause. Transverse wave, where the particles are going to move 90 degrees to the direction of the wave, or longitudinal, where the particles move in the same direction. It is possible to combine them both and get what's called a complex wave. So this is always kind of puts you in a trance because it's very relaxing. It's like looking at water waves. Take a look at the yellow dots. Do you see how the yellow dots are actually not moving very far? They're just circling. So even in a complex wave, it is possible to have no overall transfer of the mass, but transfer of the energy from one side of the page to the other. So if you don't see it yet, do you kind of see that it looks as if this wave is moving to the end? So for starters, I want you to focus your eyes on a crest and watching it move from left to right. So we say the wave direction is that way. Then look at the particles. The particles are bobbing up and down, but the particles are also going horizontally. So it's actually a circular motion. And how much transverse quality or longitudinal quality would determine whether you get something that looks more like that or more like this. Okay, now we're gonna get into the math in a little bit more detail. We still have new terms. So what is the wave speed? So before we look at that in more detail, I want you to think of measuring the distance, measuring the distance that this crest travels in 1 second. So we set up a stopwatch, and I would say go on the stopwatch. And then after a second has gone by, you would say stop, and you would measure that distance in meters. As if the crest was an object, that's one way that you could think of wave speed. Another way that you could think of wave speed, especially because this is a sound unit, the source of the sound sends the message, and you record the distance and the time to travel to another place, and the distance divided by the speed is your wave, or sorry, the distance divided by the time is your wave speed, just like we would calculate speed for an object, distance over time. Okay, going back to this gizmo, we're gonna look at what affects wave speed. And definitely this gizmo is something for you to explore. I'm gonna turn lights back on. So this is just to remind you again, that's what it looks like. We have a wave speed of 173 centimeters in 1 second. So that means in 1 second, this crest travels 1.732 meters. So now I'm gonna change things up. Let's see what changing the amplitude does. Remember, amplitude was the distance from maximum displacement to equilibrium. So if I change amplitude, how do you think it's gonna look different? Do you think the wave speed is gonna be different? So pressing play. So in order to have a greater amplitude, the person is going to have to raise their arm and drop their arm a greater distance from equilibrium. So we get a wave with a greater amplitude, but you know what? Wave speed is not affected by amplitude. In sound, amplitude is how loud the sound is. Okay, let's try, I guess we'll put that back. So we only change one thing at a time. So we get our original wave speed again. Now let's change the frequency. Now frequency haven't been something that we have formally defined yet, but if something is very frequent, that means it happens a lot. So let's increase the frequency of moving the hand up and down. So the hand is gonna move up and down faster. That also does not affect the wave speed. So the quantities that we're going to look at in more detail, amplitude and frequency, they do not affect the wave speed. But if you remember from part 1 of the lesson, that what affects wave speed is the medium or the properties of the medium. So in a spring, we can increase the tension and we get a different wave speed. Or we can also change the density of the spring and get a different wave speed. So the properties of the medium change the wave speed. So what the wave is traveling in is what determines the wave speed. Okay, so for when we are looking at a wave and taking measurements based on a wave, we can have the geometric wave characteristics, the things that we take a picture of and then you measure with a ruler, like geometry, or time-based characteristics, so things that you might need a video to kind of see. So for geometric wave characteristics, we have equilibrium, crest, which is where you have the maximum point of a transverse wave, a trough, which is the minimum point of a transverse wave, and then the distance from equilibrium to the crest or equilibrium to the trough is called amplitude. So by definition, equilibrium is exactly halfway. So it doesn't matter if you measure this or this. And let's do that measurement. The amplitude of is the maximum displacement of a vibrating particle from its equilibrium position. So we're going to draw a horizontal line to our ruler and subtract that number from the equilibrium point. So it looks like 22 minus 1 gives us 21.0 centimeters. It's the same distance as if we went from equilibrium to the trough. More geometric wave characteristics, we have the wavelength. So the length of one wave would be considered the length from crest to crest or trough to trough, or any two identical points on a wave. So the node going up to the node going up, or the node going down till the node going down. So it doesn't matter what point you pick to find how soon until it repeats. But I always think that crest to crest is the easiest, and that's maybe typical in textbooks. So in this example, we have 142 minus, I think, is that 28? So we get 114 centimeters for the wavelength of this wave. We also have the phase, which is the x coordinate of a unique point, or a phase shift if we're comparing two waves. So do you see how the dotted wave has started 40 centimeters after the first wave started? So maybe two people have their slinkies, and one person starts, and then the other person starts after this first wave has traveled 40 centimeters. So we can have a phase shift if we're comparing two waves. If two waves have the same phase, and no phase shift, they're considered in phase. So they would directly lie on each other like this. We could have two waves that are completely out of phase. Two waves are completely out of phase if the crest of one lines up with the trough of the other, or if it's not quite lined up like that, if it's like somewhere in the middle like this, we would say this is out of phase. We would say this is completely out of phase. So this is shifted a little bit, and this is shifted exactly half a wavelength. So now let's talk about, those were the geometric properties, geometric characteristics. Now we're going to talk about time-based characteristics of waves. How many times per cycle, or sorry, the time per cycle is called period, and it's in units of time, so seconds. And frequency is the number of cycles per unit time. So if it takes 1 second for 1, 2, 3, 4 waves, that means our frequency would be 4 per second, 4 waves per second. And we say hertz because that's a standard unit, for inverse seconds. What would be the period? Well, if it's 4 waves, that takes 1 second. The period would be, how long does it take for one of those? It would be a quarter of that, so it would be 0.25 seconds. We have, if these are formal, these are equations based on the definitions of period and frequency. So N is the number of events, and an event in this case is a cycle. So from equilibrium up to the crest, down to equilibrium, down to the trough, and back to equilibrium. So that would be considered one cycle. So N is the number of those cycles, and delta T is the time that matches with that. And if you notice, these two equations are reciprocals of each other. So we can actually have a main equation that doesn't have all these extra measurements, and it's just, if you know the period, you flip it to get the frequency, or if you know the frequency, you do the reciprocal to get the period. So let's do an example. Calculate the frequency and period for the following wave. Frequency is number of events divided by time. So we have 1, 2, 3, 4 full cycles divided by 1 second, so it's 4 hertz. For the period, it's how much time divided by the number of cycles. So when 1 second, we have 4 cycles, and therefore a period is 0.25 seconds. Okay, something challenging. Sketch a wave with double the frequency on the graph below. What happens to the period? So if we're going to have double the frequency, so that means in the amount of time that this wave goes crest trough, we're going to go crest trough, crest trough. So in math, if you've gotten to this point in the grade 11 math course yet, this is called a horizontal compression. All the points get 2 times closer to this axis here. And we have time divided by number of events has to be double, or sorry, the number of events has to be double. So that means our period is 0.125. And that also is in line with the 1 over f. So if you do 1 over a number versus 1 over double that number, the value of the fraction is going to be halved. Wave speed is something that ties together geometric properties and time-based properties. So wave speed is a measure of how fast the energy of a wave is moving in meters per second. Wave speed is equal to frequency, which is time-based, and wavelength, which is geometry-based. And if you look at the units of frequency, inverse, like cycles per time, and then lambda, wavelength, is distance over time. Oh, I don't know if I remember actually saying wavelength is the symbol that is used for wavelength is Greek letter lambda. So you might want to practice drawing this out for your notes. It's kind of like a fancy Y that's upside down and flipped. So flipped horizontally and vertically. So lambda. Lambda is the wavelength. So it's the distance for one cycle, and unit analysis tells us cycles canceling out, you get distance over time, which is just regular units of speed. Okay, let's try an example. So what are our givens? We are given the wavelength and the frequency, and we want to find speed. So we substitute into our universal wave equation. V equals F lambda, and we get 506 meters per second. And then to round to 2 sig figs, that would be 510 meters per second. The speed is determined by the medium. So this comes up in this overall message comes up in so many times in this unit. So it's a really important one. All mechanical waves in one medium at a certain temperature and density move at the same speed. Frequency is determined by the wave source. What affects wave speed? The speed of a wave in the medium is related to the intermolecular forces between the particles of the medium. The larger the attractive force between particles, the faster they will return to rest position. So the faster the speed of the wave. This is why waves travel faster and farthest in solids, slower in liquids, and slowest in and shortest in gases. Okay, hopefully we're back at the slides. Okay, back at the slides. Okay, speed of sound. There is an equation that connects the wave speed, when we're talking about sound, to temperature of the air. Waves travel faster in hotter air than in colder air because there's an increase in molecular motion caused by the higher temperature. So for example, if you are, for every 1 degree Celsius that you increase the air, sound is going to travel 0.6 meters more per second. So if temperature was 0 degrees, then this whole term would cancel out, and we get 331.4 meters per second for the speed of sound in air. That means if you shout out on a cold 0 degree day, you shout out something. In 1 second, your voice will travel 331.4 meters. So let's try this, although I do have this written up for a much colder day. So remember way back when it was 4 degrees Celsius, we haven't seen, we're so lucky we have beautiful weather. We haven't seen that temperature in a little while. So we substitute into the wave speed equation. This is the wave speed equation only for sound in air at different temperatures. And that calculates to be, on our calculator, 331.824 meters per second, which gives us a final answer of 330 meters per second when you consider the significant figures. So just to reiterate that this equation is for sound based on temperature. Another kind of wave that you might have is the wave on a string. And the speed of the wave on the string depends on something called the linear density and the string's tension. So we've learned about tension before, FT. We've never learned about linear density. Linear density is the object's mass divided by the length. And the symbol is mu, just like the coefficient of friction. Do you guys remember the coefficient of friction from way back in Unit 2? So unfortunately, it's the same Greek symbol, but hopefully you'll recognize that this is linear density is relevant for Unit 5. So speed is square root of Ft divided by mu. And you have to use SI units for all of these quantities. In this example, we have a guitar string, and we want to find the tension in the string given the mass, length, and the wave speed in the string. So we can connect mass and length to get linear density. Mu equals 0.35 kilograms divided by 2.3 meters. Guess, did you see that I converted right away to SI units? It has to be SI units. Mu is 0.152 kilograms per meter. And then, that's not what's being asked. We're asked for Ft. We can rearrange the second equation, the real equation for wave speed, for wave on a string. Square root of Ft divided by mu, we can rearrange this for Ft and get 380 newtons. So we're going to have to rely on our calculated answer. It's really important that you use an unrounded number when you're carrying it forward. And that we round our final answer to 2 significant figures. So we've learned a lot of new terms and a few new equations, so it's time for you to practice. These are a whole bunch of really short questions, so none of them should take you very long, but it's important to do all of them. We have an exit ticket for this video on Google Classroom, and please submit these practice questions when you are done. Have a wonderful day.